Hello, welcome to this video. This is 4-4 and we are talking about related rates, a big topic in calculus and one that is usually assessed on the AP exam. We're going to go ahead and look at rates of a contextual example. We're going to differentiate often with respect to t, time, so implicit differentiation is usually involved in this topic. All right, let's go ahead and jump off our lesson at that point. They say consider the curve defined by x squared minus 2y plus 5x is equal to y cubed minus 6. Find dy dx. So what we're going to go ahead and do here is we are going to implicitly differentiate with respect to x. So 2x minus the derivative of negative 2y is negative 2 times the derivative of y, which you can use Newtonian notation, so dy, y prime, or you can use Leibniz notation, dy dx, plus the derivative of 5 is equal to 3y dy dx. Okay, and now I want to go ahead and gather my terms on the same side. So we have negative 2 dy dx minus 3y dy dx, and we're going to move the 2x and the 5 over. Okay, at this point we'll go ahead and we'll factor out our dy dx, giving us negative 2 minus 3y is equal to negative 2x minus 5. And then I can go ahead and I can divide each side by negative 2 minus 3y. So we get negative 2x minus 5 is equal to negative 3y minus 2, and I just shuffled those. I did have some students say, hey, I want to factor out that negative. Can I take out a negative out of both? And the answer is yes. This is also correct. If I factored out a negative and then canceled them from the numerator and the denominator, 2x plus 5 over 3y plus 2. All right, so that is implicit differentiation, and we differentiate with respect to x. But we can also go ahead and differentiate with respect to any variable, even if that variable is not in the equation. Okay, and we often do this with the variable t, time. Okay, so let's go ahead and let's look at an example of this. Example number 1, they say consider y is equal to 2x cubed minus 4x plus 3. Differentiate with respect to t. Differentiate with respect to t. Okay, so every time I take a derivative, and if it's not t, I have to multiply by the derivative of that variable with respect to t. So an example, the derivative of y is 1 times the derivative of y with respect to t. So dy dt. That's just that chain. Okay, the derivative of 2x cubed, well, that is 6x squared times the derivative of x with respect to t. So dx dt. And now I'm treating x as if it were a y when we were differentiating in the example above. Okay, minus the derivative of 4x, well, that's minus 4 times, again, dx dt. And if you wanted to go ahead and simplify this, you could factor out your dx dt times 6x squared minus 4. Okay, so that is differentiating with respect to a variable that is not present. Okay. Example number 2, same idea. Consider 5p is equal to q squared minus sine of q plus e to the power of 3q. Differentiate with respect to z. Okay, sure. All right, so this is 5 dp dz, which is equal to 2q times dq dz minus derivative of sine is cosine, so cosine of q times dq dz plus the derivative of e to the power of 3q is e to the power of 3q times the derivative of the power, which is 3, times dq dz. Okay, so there it is. That's differentiating with respect to a variable that's not present. Anytime you're differentiating with respect to a different variable, you have to multiply times the derivative of that variable with respect to whatever it is you are differentiating. Okay, now let's go ahead and see how this ties into implicit differentiation. We're going to be given some, sorry, not implicit differentiation, related rates. We're going to be given some examples that are similar to related rates problems, but we just don't have that context. So let's go ahead and look at the first example here. Example 3. Given x squared minus y cubed is equal to 7, find dy dt in terms of x and y if dx dt is equal to 4. Okay, so I'm going ahead and based upon this, I need to find dy dt. I'm differentiating with respect to t. So let me differentiate. We have 2x times 2x dt minus 3y squared times dy dt, which is equal to 0. So now they say, okay, well, what if dx dt is 4? So we can go ahead and substitute that in here. So 2x times 4 minus 3y squared dy dt. And again, I need to go ahead and find dy dt. So this is, it looks like, negative 3y squared dy dt is equal to negative 8x. I just multiplied the 2 and the 4 and moved it to the other side. So I have negative 8x. And thus, in terms of x and y, dy dt is equal to negative 8x divided by negative 3y squared. And of course, we can cancel out those negatives to give us 8x over 3y squared. Okay? Awesome. Example 4. Given the natural log of 3x squared plus 4x is equal to cosine of 2y, find dy dt in terms of x and y if dx dt is equal to negative 3. I'm going to go ahead and pause this video. I want you to try this example, and then I'll show you the example or the answer here in a moment. Alright, so here is the solution to the last example. I went ahead and differentiated both sides. So we had 1 over 3x squared plus 4x times the derivative inside. So I have 3x squared plus 4x, the derivative of that would be 6x times dx dt plus 4 dx dt. Okay, and if you went ahead and factored that out or you multiplied by it after, you could go ahead and do that. And then I just moved them into, moved this expression into the numerator. And this is equal to negative 2 sine of 2y dy dt. And then I went ahead and just divided both sides by negative 2 sine of 2y. And here is our solution. All right, so there you have it. Very good. And I substituted the dy or the dx dt, which is equal to negative 3 here. You could go ahead and distribute that in if you wanted to, but there you go. All right, so let's dive into related rates. What the heck is related rates? Well, in math, two variables are related if one variable affects the other. And we see this in various formulas. And we'll take the example of a circle here for a moment. Consider the circle above with a radius r. We know that the radius of the circle is related to the area. Now, when the radius changes, we also know that the area changes. And thus, the area and the radius are related by this formula. Area is equal to pi radius squared. And as r increases, area also increases. But what's the relationship? How are they increasing related to each other? Well, this is the idea behind related rates. Just as two values can be related through equations, the derivatives of those values are also related. Finding how those rates are related requires differentiation with respect to a given variable, and it is often time. So let's go ahead and let's look at example number 5 here. Let's go ahead and look at a situation. All right, so the circle above is expanding and contracting. They say in A, find an expression for the rate that the area is changing with respect to time. Well, you need to know what the formula for area is. So I have area is equal to pi r squared. So area is equal to pi r squared. Well, now if I go ahead and differentiate this with respect to time, we get the derivative of A with respect to time is equal to 2 pi r, that's just power rule. Now I'm going to multiply times the derivative of r with respect to time. So there is an expression for the rate that the area is changing with respect to time. B, the radius of the circle is increasing at a rate of 4 centimeters per second. Well, what they just told us there is that dr dt is equal to 4 centimeters per second. That is how the radius is changing, that its rate of change. Now, if it were decreasing, that quantity would be negative. Here's their question. At what rate is the area of the circle increasing with respect to time when the radius is 7 centimeters? So I'm going to go ahead and I'm going to use my formula that I just had. dA dt is equal to 2 pi r dr dt. And then now what I'm going to go ahead and do is I'm going to use the given information and I'm going to solve for the question that they want us to find, which is what rate is the area of the circle increasing? Okay, so I am solving for dA dt, and now I'm just going to go ahead and plug in my values. So 2 times pi times r. They say when the radius is 7 centimeters. So they finally give me that. So I plug that in when I am evaluating after I have differentiated. So 7 times the derivative of r with respect to t. Well, they gave us that. They told us that the radius is changing at a rate of 4 centimeters per second. Okay, so here is dA dt, and this was in centimeters, this was centimeters per second. And if I go ahead and multiply this, we have 14 pi times 4, and that's going to, I don't want to lose track of my units here. This is in centimeters times 4 centimeters per second. And if we go ahead and calculate this, this gives us 56 pi centimeters squared per second. Okay, so that is how area is changing with respect to time. All right, C. The area of the circle is decreasing at a rate of 10 centimeters per second. dA dt is equal to negative 10 centimeters squared per second. At what rate is the radius of the circle changing when the radius is 3 centimeters? Okay, so they want us to find what is dr dt when the radius is equal to 3 centimeters. That's what we need to find. Okay, so again, I'm going to use the equation that they gave us. So dA dt is equal to 2 pi r dr dt, right? So I'm using that formula of area and radius, how they are related. Okay, and I'm going to go ahead and I'm just going to plug this information in now. So we had negative 10 centimeters squared per second is equal to 2 pi times the radius. They want to know how is the radius changing when radius is 3 centimeters. So 3 centimeters times dr dt. Okay, so if I go ahead and solve this, I'm just going to divide each side by 6 pi centimeters. Divide by 6 pi centimeters. We get dr dt, I'll put it up here, dr dt is equal to negative 10 over 6 pi centimeters per second. So that is how it is changing. And if we wanted to go ahead and reduce here, we could. This would be negative 5 over 3 pi centimeters per second. All right. I'm going to go ahead and break up this video. The next videos will dive into actual related rates questions. This was more of an introduction. So go ahead and give me a thumbs up, like this video, subscribe to see more related rates videos. Catch you in the next one.